You very much, Roman, for the kind introduction. I hope you can see my slides. And let me also begin by expressing my thanks for the invitation to speak to this group. It's a very exciting work that you are all engaged in, and I look forward to interacting with you all. So the what I will present today is basically a subset of the work that is going on in my group, where our goal is to take some emerging spintronic devices, in particular magnetic tunnel junctions, of which there are a few different flavors that I will introduce along the way, and to use them in conjunction with conventional digital CMOS integrated circuits to do probabilistic computing. Um, so the key elements of the work that I will describe are basically the first two papers that are highlighted here on this page. And the third one is a more device-oriented work that is very recent. And if there is time, I will briefly touch upon that and its relevance to probabilistic computing as well. I should begin by saying that by training, I am more of a device engineer, and I come from the magnetics and spintronics background. But I hope that I can still make this presentation engaging and interesting for all of you. Um, so this is the outline. So I will briefly present what I mean by probabilistic computing and probabilistic bits, which are kind of the fundamental building blocks of probabilistic computing. And then basically, I will spend some time showing a few different ways of realizing these probabilistic bits and computing systems based on them. The first one, which is fairly established by now, uses devices called stochastic magnetic tunnel junctions, which are designed to be unstable, to be very susceptible to thermal noise. And so they can act as sources of randomness to execute probabilistic algorithms. I will use that example to kind of show the limitations of that approach and why we are interested in using other types of more recently developed magnetic tunnel junctions. And I will highlight some work that we've done with what we call voltage-controlled magnetic tunnel junctions in particular, both at the device level in conjunction with software, and then I will show a CMOS ASIC that we designed and interfaced with some of these voltage-controlled magnetic tunnel junctions. Then I will show some work that we've done over the past couple of years to extend the formulation formulation of the variables from probabilistic bits to what we call PDITs, d-dimensional probabilistic variables. And I will show some examples of how this can speed up the solution of combinatorial optimization problems and how it can allow us to create energy landscapes that are much easier and more efficient to explore. So let me begin by showing the motivation. So one way to motivate why we need probabilistic computing is that if you think about the conventional way we do computing, it's essentially based on deterministic algorithms on von Neumann machines. And this works well, but for certain problems, it has a significant challenge in the sense that um, the resources you need to compute grow exponentially. And for certain problem sizes that are of practical interest, it is difficult to solve these in a deterministic way. And so this is where the idea comes in, whether we can use probabilistic algorithms in order to solve them. At the risk of oversimplifying things a little bit, I can add that these problems generally have a flavor where solving them in one direction is efficient, but solving them in the other direction is not. And so an easy example of that is finding the product of two numbers. Multiplication is easy. Factorization is very difficult. More generally, if you had some Boolean statement, which is what I'm showing here on the top left, and you knew the inputs and you wanted to know what the output is, whether it's true or false, that is easy to calculate. Whereas if you wanted to know how many combinations of the inputs would make that statement true or false, that is generally a Boolean satisfiability problem, which can grow very unfavorably. And so it becomes difficult to solve it beyond a certain point. So the general idea of probabilistic computing, or more precisely here, probabilistic Ising machines, is that we can use energy minimization by drawing inspiration from physics, is to build machines that essentially do energy minimization. And we know, of course, from physics that any physical system likes to, in the limit of, if you essentially let it evolve long enough, it likes to go to its ground state. And this is this is something that in probabilistic Ising machines we basically use to our advantage. So the idea is we construct an energy landscape, which is what I'm kind of schematically showing here on the bottom right, that is defined by a number of probabilistic variables, MI, which is what I'm showing here on the left. These probabilistic variables essentially are bistable, so they are bits in that sense, but they are probabilistic. They spend some of their time in the one state and some of their time in the zero state. And the amount of time that they spend in one state or the other is sensitive to an input, which is this parameter I sub I here. So there are two essential elements to a probabilistic bit or p-bit then. One is the randomness element, and the other one is some nonlinearity, some bias superimposed upon that randomness. Then if you have such probabilistic bits, you can connect them and create essentially a network of those defined by a matrix J, which is again shown here in the Hamiltonian on the right, which essentially is inspired by the exchange interaction of magnetic systems in physics, and a vector H sub I here, which adds a bias upon each of these probabilistic bits. So by defining these J and H matrices, we essentially define an energy landscape. And then the hope is that we let this evolve either by itself or more likely with some sort of annealing algorithm where we find the energy minimum. And if we've defined this energy landscape correctly, that energy minimum will correspond to the solution of our computing problem. So the question then is how to realize these p-bits, and there are many physical principles that can be used for this. You can realize these entirely in digital CMOS, and I will show an example of this later on. But of course, we are interested in realizing these p-bits in a way that is area efficient, energy efficient, and also fast, where we have a high throughput of random bits coming out of them. And one way to do this is to use these devices we call magnetic tunnel junctions. So a magnetic tunnel junction, which is this thing that I'm pointing to here on the left. I don't know, by the way, if you can see my pointer while I'm presenting.
Yes, we can
You
see it.
can. Okay, that is great.
Yes.
So basically, the magnetic tunnel junction is what I'm highlighting here. So essentially, it's three layers. Usually, each of these has sublayers within it, but it can be boiled down to two ferromagnetic layers separated by a dielectric in between. So the conduction between these two ferromagnetic layers occurs through tunneling. There is an effect referred to as tunneling magnetoresistance, or TMR for short, whereby if the two layers have a parallel magnetization, the resistance is lower. And if they are anti-parallel, the electrical resistance measured across this tunnel junction is higher. So the relative difference between these two is called the TMR ratio. And so the TMR is basically what allows us to convert magnetic information, which is basically the state of one of these layers, whether it's pointing up or down, into an electrical signal, an electrical resistance that then with some circuitry we can convert into a digital voltage. The other important part of this device to remember is that there is an energy barrier that separates the two states. This comes from the magnetic anisotropy of the material. And conventionally, if we want to use this magnetic tunnel junction for memory, we would design this energy barrier to be large so that the thermal energy from the environment is not likely to switch the device. However, in the context of this talk, I will be focusing on situations where this energy barrier is intentionally small, either statically small or where we lower it by applying a voltage so that the device exhibits stochastic behavior and generates random bits for our computing purposes. So let me then, after that brief introduction, show you a very established way now of realizing probabilistic bits using magnetic tunnel junctions. This is essentially, as I alluded to in the previous slide, where we designed a device such that this energy barrier separating the anti-parallel and parallel states of the magnetic layers is small, on the order of, say, a few kT. And what that will do is that it will allow thermal energy from the environment to provide sufficient energy to the magnetization to overcome this barrier with a mean dwell time, a mean retention time that is tunable by the size of this energy barrier. So this device will essentially turn thermal noise from the environment into a random bit sequence. What you can do additionally is that you can drive a small current through this device where, depending on the direction of the current, the device will favor one state over the other. So it will spend more time in the AP state versus the P state, or vice versa. So with this, then you can realize probabilistic bits and related ideas. For instance, here I'm highlighting the paper from several years ago where we used 6 such magnetic tunnel junctions to do stochastic computing to realize a small neural network. I'm showing here on the right measured probabilities of bit streams measured from such a magnetic tunnel junction, where you can see that depending on the voltage that we apply to this device, we can essentially tune its probability from spending essentially all of its time in the anti-parallel state to, on the other extreme, spending all of its time in the parallel state. And in the middle, around 0 volts, it basically is roughly half-half. And so it's really a random bit sequence. So this can be realized also, can be used to realize probabilistic Ising machines. And there is a lot of very nice work going on using this approach. But this is an approach which we fairly quickly realized has some serious scaling challenges. Let me briefly tell you why that is. So the first reason that this approach encounters a scaling challenge is the fact that if you rely on the presence of a very small energy barrier that needs to be fine-tuned, of course, this works well for one device, but you can imagine that in a real chip that is trying to solve large-scale problems, you may have millions of these magnetic tunnel junctions. And so there's going to be a distribution of this energy barrier. It's not going to be the same for all of the devices. And since the mean retention time of this device depends exponentially on this energy barrier, this creates a very big problem. So some of your probabilistic bits will be very, very stable, and others may not even have any stochasticity to them. The other issue is that you need a digital to analog converter for each individual probabilistic bit because these are essentially analog devices. The input that defines the probability profile, the nonlinearity of the p-bit, is essentially this current that we're driving through this device. So you need a digital to analog converter for each p-bit, and this consumes a lot of area. And also, these nonlinear transfer curves are, of course, not identical for different devices. And as a result, this also needs quite a bit of calibration. And while there are ways being explored around each of these, and some of them we have explored, for instance, by looking at different ways of doing the annealing so as to guide the energy minimization process along the way. And some of these approaches do reduce the sensitivity to device variations and so on. I'd like to focus on a very different approach that really fundamentally overcomes these challenges that I just mentioned. So this is basically the idea here is to depart from magnetic tunnel junctions that are current controlled, which is what I showed you here, to magnetic tunnel junctions that are voltage controlled, that are essentially electric field sensitive. And the basic physical mechanism, I won't go into the details of it, but it is essentially the fact that for appropriately engineered materials, that energy barrier that I showed you in the previous slides can be sensitive to the voltage applied to the device. So it's not a static thing, and its sensitivity to voltage can be engineered. And so what we learned from that is that it is not necessarily the case that a magnetic tunnel junction needs to be designed to be permanently stable or always stochastic. This is something that we can tune depending on need in a circuit. So we can really control the energy barrier depending on how we are using these magnetic tunnel junctions. And the idea is shown here, basically. You have essentially that same energy barrier that I was showing you in the previous slides. With a voltage, here we reduce this energy barrier so that in the presence of voltage, you only have one energy minimum, which is sitting in between the two stable magnetization configurations in the absence of voltage. Once you remove the voltage, you basically have a situation where the magnetization can fall into one energy minimum or the other minimum with equal probability. And so this will be a 50-50 random bit generator. The nice thing about it is that there are two things that are nice about it. One is that it's very fast. These entire dynamics happen on the order of a few nanoseconds. And so you can fairly easily get a new random bit from a single MTJ every, say, 5 to 10 nanoseconds or so. And these are very compact devices. You don't need a lot of circuitry in order to read out the state. And so if you then build small arrays of these magnetic tunnel junctions, you can get to very high throughput random bit generators in a fairly small area. I'm showing here a random bit sequence or random resistance measurement from a device from one of our early measurements where we showed that this indeed works. Now, the question is then, how can I do probabilistic computing with this? Because if you followed the reasoning of the previous slide, basically what I showed you is essentially a coin flip device. It's a device that generates random bits, but they're really random with a 50% probability. And one of the things about these voltage-controlled magnetic tunnel junctions is that since they are voltage-controlled, we designed them to be more like capacitors. So they have a very high resistance, unlike spin transfer torque magnetic tunnel junctions that have low resistance. Which means that we cannot, at the device level, really tune the probability in any efficient way. What we found was that this is not necessarily a big problem. As I indicated a couple of slides ago, the tunability at the device level, tunability of the probability at the device level, we don't really think is a strength of magnetic tunnel junctions, precisely because it comes with this requirement to have individual calibration for each device. And so instead, what we decided to do with these devices was to really use them as coin flip devices. So essentially use them to create the randomness element of the p-bit and to implement this nonlinearity that is superimposed upon it using a lookup table in digital CMOS. And since these lookup tables can be shared between a fairly large number of p-bits in any typical way that you would design this, this doesn't really add a lot of area overhead. So the first experiment we did where we attempted to compute something with magnetic tunnel junctions of this kind is kind of summarized here. So this was basically in this experiment, we took a voltage-controlled magnetic tunnel junction. We measured long random bit sequences generated by voltage, tens of millions of bits. And then we used these in software, using these experimentally measured bit streams, to realize a simple probabilistic Ising machine. And so the first thing we did was to see if we can realize invertible gates. Indeed, this worked, as I'm showing here on the top. So here I'm showing an invertible AND gate, which is essentially a gate that probabilistically follows the truth table of an AND gate. If you set it to inputs, of course, the output will spend most of its time in the logical state that is consistent with those. But you can also use it the other way around. So if you clamp its output to one state or the other, the two inputs will arrange themselves such that they spend most of the time in the states that are logically consistent with that output. So for instance, here I'm showing an invertible gate with the output clamped to 0. And since this is an AND gate, this means that the inputs could have been 0, 0, 0, 1, or 1, 0. And so the gate spends 1/3 of its time in each of those states. And if you set the output to 1, of course, the two inputs should always be 1. Now, at the level of an individual gate, this is not terribly interesting. But since we know how to construct more complicated circuitry using these logical gates as building blocks, we can also do more interesting things. So for instance, we can build an invertible multiplier, which is the same thing as a factorizer. And so this will be a circuit where if you use it in the forward direction, you can provide the inputs and it just multiplies. Or you could provide the output and the inputs will spend time in the states that are logically consistent with that output, which are basically the factors of that multiplication result. So I'm showing one example here. This is a 40-bit factorization example using, again, this approach, experimentally measured bit streams from MTJs, but the rest was really all implemented in software here. So this was a good learning experience for us, really, to understand how this mapping works from different computing problems. And again, I'm showing factorization only as an example here to these probabilistic Ising machines. But of course, where we want to go eventually is to build ASICs that combine these entropy sources, randomness sources, such as magnetic tunnel junctions with CMOS, and in a way so that the digital CMOS circuitry and the devices are co-designed so that you get the most performance out of this. And so our first baby step towards doing this really was what I would like to briefly show you next. So here what we did was we basically have a voltage-controlled magnetic tunnel junction chip, which is what I'm highlighting here on the top right. This has around 2,000 or so voltage-controlled magnetic tunnel junctions on it. These are wire bonded to a holder, and then we have some simple circuitry on this board that allows us to pulse them and to read their state. And then we have an ASIC here, which is in ancient technology, 130 nanometer CMOS. And it's basically a digital chip that contains two parts. It has a RISC-V controller that basically controls the whole system. It controls when you pulse the voltage-controlled MTJs. It reads the states of those V-MTJs from the adjacent board. And then it feeds it to the core of this thing, which is what I'm calling here the PIM design area, the probabilistic Ising machine design area. What this PIM design area contains is essentially the p bits, the J matrix, the H vector, the lookup tables, all of those things that essentially make up this probabilistic Ising machine and implement these using these random bit streams read out from the adjacent voltage controlled magnetic tunnel junction. So for this first experiment, what we decided, again, was to focus on factorization. It's not that we're terribly interested in that particular problem, but factorization is interesting because it only has one correct solution. And so checking the quality of the solution is very easy. This is not necessarily the case with many combinatorial optimization problems that I will briefly talk about later on as well. In this chip, again, I will show you other flavors of this later on. What this chip was essentially a series of invertible multipliers of the same kind that I showed you a couple of slides back. So these are some results from this chip or from this system, really hybrid two-chip system. So you can see here on the top left, basically a summary of the annealing schedules that we did on this. So there is a mathematical temperature that is implemented that can be scaled, that can be controlled. And so we can basically control how the basically what the mathematical temperature is that these p bits are experiencing, which in turn affects their retention time or how often they are likely to change states. And with this, then we basically optimized, sort of arrived at an optimized simulated annealing schedule for the types of problems we were looking at. Then I'm showing you three things for very small problems. So it's a 6-bit factorization, 35 equals 5 times 7, where I'm showing you that these circuits can basically do all three operations equally well. So they can do multiplication, they can do division, and they can do factorization. And again, because the whole thing is based on invertible gates, it doesn't really show much of a difference in terms of which way you're running the circuitry. You can track the mathematical, really, the energy of this system, defined by that Ising Hamiltonian that I showed you several slides back, as a function of time. And you can see that indeed it is searching through the solution space, and at some point it basically reaches its minimum. The size of the problems that we can address basically depends on the number of p bits that we implement. So it's a function of transistor count and also a function of the bit rate with which we generate these random bits. So in this example, this was basically our first attempt where we did 6-bit factorization. We then learned quite a bit from this first design, and then we were able to improve it. So really, this paper that I'm highlighting here summarizes results from 2 chips. And the second one had a number of improvements that allowed us to really search through this energy landscape much faster. And it was able to solve problems up to 24 bits in size. And I'm showing you one example of that here. Again, these are still relatively small problems, so they're not really of any practical relevance. But we took a look next at how big of a problem we think we can really address if we use the more advanced node, because as I mentioned, both of these chips were realized in 130 nanometer CMOS, so the transistor density was very, very small. And so that's kind of the result of that exercise are shown here. And these are basically projections based on a number of different PDKs mixed here. But what you can see is basically that, not surprisingly, if you go to more advanced nodes, the higher transistor count allows you to realize more p bits within a, a certain available area. And this then allows you to also attack larger problem sizes, except here expressed in the number of bits. So these could be the number of bits of a number you're trying to factorize, or it could be the number of bits in some optimization problem that you're trying to solve, for instance. I should mention that this analysis it's not really about the speed with which we can solve these problems. That depends really on the annealing schedule and on the mapping and so forth. It only expresses basically how big of a problem can be fit into what area in uh, in conventional foundry CMOS. And so the point we were trying to make here was that really fairly large problems are entirely within reach, at least as far as the mapping to silicon is concerned in digital CMOS. And then, of course, as I will show you partly in the next slides, there is a lot of other design considerations that go into the question of, well, once you've done the mapping, how fast does it actually solve the problem? So just briefly, I should mention that now we are working on more advanced versions of these chips in 40 nanometer CMOS, as well as trying to integrate the magnetic tunnel junctions on the CMOS. So we should hopefully soon be able to say more about that. So for the next few minutes, I'd like to now switch gears a little bit from the so far mostly hardware and very much device-focused nature of what I presented to taking a look at actually these variables themselves, these probabilistic bits, which have been kind of the building blocks of everything that I showed you. Probabilistic bits are essentially two-dimensional stochastic elements. And for many problems, they work very well. But there are many real-world problems that are of practical interest where probabilistic Ising machines may have a value proposition, where these problems just do not naturally map well into a binary formulation. As I will show you shortly, are integer programming problems. So you have variables that are naturally integers. And so you need to do some work, some processing in order to translate this into the bit domain and then to translate it back. So what we thought here was, well, perhaps we don't really have to confine ourselves to p bits as the fundamental building blocks of probabilistic computing. And somewhat loosely inspired by the idea of qubits in quantum computing, we defined this thing that we call p-dit, d-dimensional or higher dimensional probabilistic variable. So a p-dit is essentially a variable that has an arbitrary number of dimensions and an arbitrary number of states per dimension in the most general sense. So you can basically tailor the number of dimensions and the number of states in each dimension, as well as the update rules, how it moves between these available states, in a way that fits the nature of the problem that you're trying to solve. And within this very large space,
Oh,
see him online. Roman is online now. So, Roman,
Uh,
so Sasan, we are not the host, right? Roman can
no.
only do the
Yes,
recording. Is
yes,
that?
I'm back.
Yes. Let me try to see if I can record on my side.
okay.
But I think it's
Okay.
being recorded.
Yeah, I cannot. I can
I mean,
send the
I'm back,
request.
so it should resume recording if you can hear me.
Okay.
Okay, great. Okay, so let's continue that. Within this landscape of p-bits, then you could think of a p-bit as basically a small subset of this, right? So it's essentially um, either a two-dimensional object with one state per each dimension, or a one-dimensional object with two states along that dimension, which are basically equivalent to each other. But there are also other types of variables that you could define. For instance, you could define isotropic p-bits, which are essentially n-dimensional, but they only have a single state per dimension. And this is very useful for things like traveling salesman problems or related problems. Um, and you could also define arbitrary number of states for a one-dimensional variable. So, for instance, you could define what we call p integers or p ints, where you have a range of integers, um, which basically are all along the same dimension between two bounds A and B. Uh, and um, and then each update for this variable would consist of, with some probability, the variable staying in its own state, going up by one, or going down by one. And so the detailed formulation of this, both the general case and the two cases of isotropic p-dits and p-ins, is explained in this paper that we published last year. And we think that there are many different versions yet to be explored of this p-dit idea that could be tailored to different problems. And we're working on some of them with collaborators. But let me just show you one example of where we think this is particularly powerful. These are integer programming problems. So integer programming has many real-world optimization problems that are basically integer programming in nature. These relate to logistics, scheduling, manufacturing. These are problems where you have naturally integer variables. For instance, the number of containers in a ship, or the number of cars produced on a certain assembly line, or things of that sort. And the general nature of these problems is that you're trying to find an assignment to a collection of integer variables. You're trying to maximize some objective function while observing a series of linear constraints. And this is why they're called linear integer programming in that case. The difficulty of these problems comes precisely from the fact that these variables need to be integers, and that makes these difficult to solve in general. So if you think about a problem like that, and I'm showing you here the constructed energy, the basically the constructed energy landscape of a constructed problems, just for illustration. Um, what you will notice is, if you look at this panel at the bottom, suppose, for one of these variables, it can have a range of between 0 to 7, just for the sake of argument. And let's say the optimum value that you're searching for is 4, right? And let's say we are searching through this energy landscape and we have arrived at the number 3. And so we are very close to the solution, but we're not there yet. if you've used p-bits in order to formulate this problem, what happens is that you need 3 p-bits in your Ising machine to flip in order for you to go from 3 to 4, which is your solution. And what this means is that in the energy landscape, you will basically have a large energy barrier between a state that is nearly your solution and a state that is actually your solution. And so this will make it very difficult and very time-consuming, therefore, to actually reach the solution. And so you can see this in these top panels, where I'm showing essentially that searching using a p-bit formulation through the energy landscape is inefficient. So it doesn't really reach into part of your energy space, whereas with integer variables, you can. If you define your probabilistic integer to be a number between 0 to 7, and you define your updates to be going up, going down, or staying in the state where it is, it takes only one update of your probabilistic variable in order to go from a solution that is nearly optimal to a solution that is actually optimal. So we implemented these p-ints and p-dits using a series of different hardware platforms. We do this on CPUs and on various FPGAs that we have. But we also designed a small chip that basically implements p-bits, p-ints, or 3-dimensional p-dits, just so that we had a platform where, at least for relatively small problems, we can do a fair comparison of all 3 of these. So again, we looked at many different problems using these formulations, and this is all summarized in the paper that I'm showing here on this page. But just to highlight one example, and this is integer quadratic programming, where the objective function is quadratic. We were able to show that, at least compared to openly available state-of-the-art software solvers that we were able to get with an academic license, we perform equally well, or in some cases, significantly better than some of these using a p-int probabilistic Ising formulation. And so we think that this is a very potentially fruitful way of looking at realizing probabilistic Ising machines in the future, where we do not have to limit ourselves to p-bits any longer. We are now also extending this formulation and applying it to a number of large-scale optimization problems in a variety of different areas, and it's looking very promising, and hopefully I can show you more results on that at the next opportunity. So this is really the bulk of my talk. I'd like to maybe just spend 1 minute to tell you about some really exciting device level work that we have done that I think will be a huge opportunity for probabilistic computing, but also for many other applications of magnetic tunnel junctions, such as memory and other areas. And this is basically using devices that are based on antiferromagnets rather than ferromagnets. So antiferromagnets are materials that have essentially no net magnetization. Their neighboring spins are exactly antiparallel to each other. And for a long time, it was thought conventionally that they're completely useless as information storage elements, because you can't interact magnetically with something that doesn't have a magnetic moment. But in recent years, we and others have learned that this is in fact not true, and it is possible to interact with these devices and to read out their state and to write information into them. And we think that this will lead to magnetic tunnel junctions that could be potentially 2 to 3 orders of magnitude faster than the ones we have now, and more importantly, that are immune to external magnetic fields. So their states cannot be disturbed, and errors cannot be caused in the states by external magnetic fields. I will flip through the more physics-oriented slides just to show you the end results. These are some magnetic tunnel junctions actually produced on 200 millimeter wafers with some of our industry partners, where the materials are completely different from the magnetic tunnel junctions we use today. They have no net magnetization. They're completely immune to external magnetic fields. And yet, we see TMR ratios as high as 360%. We can switch these with current. And in fact, this led us to discover a fundamentally new current-induced torque in these antiferromagnetic systems that we call octopole-driven spin transfer torque, or OTT. So in the interest of time and seeing as we're approaching the end of the hour, I will just thank all of our sponsors and all of my students and postdocs who contributed to this work. And I will just leave the summary up here, and I'm happy to take any questions you might have.